Welcome to the HBM Test and Measurement FAQ video series. I am Mike Hoyer, HBM Applications Engineer, and in this video I'm going to provide an overview on Perception's STL analysis option for switchgear testing. Switchgear testing involves the testing of various switchgear, such as circuit breakers or fuses, to improve and maintain the safety of people and the environment. Switchgear testing is a very demanding application involving high currents that are interrupted while high voltages are present, creating high electromagnetic fields. As a result, it requires specific hardware and software to produce safe, accurate, and reliable results while meeting international standards. HBM offers a long-time proven hardware solution specifically designed to withstand severe electromagnetic environmental conditions, known as the Genesis HighSpeed Data Acquisition System, offering near-infinite isolation via a battery-operated fiber-optic isolated digitizer, plus the Genesis HighSpeed Test Sequencer for accurate sequence and timing of events with fiber-optic isolated outputs and inputs. Now, to complete the solution, HBM offers a long-proven software solution known as Perception, offering fast, accurate, and repeatable results in compliance to relevant standards such as STL, the Short Circuit Testing Liaison Agreement, and UL 489, plus recovery voltage and asymmetric and symmetric current analysis. Now, in this short video, we're going to demonstrate some of the unique and vast automated functionality of Perception's STL switchgear analysis capabilities. Perception's STL option allows you to easily create and automate your own custom switchgear analysis equations using a vast proven set of internationally recognized STL switchgear functions to quickly calculate all the results you need. Now, Perception can easily be set up to acquire your data, then automatically perform all the switchgear analysis, display your waveform and numerical results, and even generate your own custom professional report. No more need to perform analysis manually. Now testing can be completed in a matter of seconds. In the right column, you can see a list of some of the STL functions for high voltage, medium voltage, and low voltage switchgear analysis. Now, these include basic STL functions based on the STL technical report. Generic functions, which include signal start and end, next, previous, zero crossing, crest value, and true RMS. TRV functions are transient recovery voltage functions. STC, or short time current functions. And mechanical timing test functions. Now, we've also added STLX functions based on UL 489, and these include symmetrical asymmetrical power factor functions, as well as functions for crests, frequency, and envelopes. Now, there are several ways you can automate and customize your STL switchgear testing and analysis within Perception. For high voltage applications, you can choose the HPHV or high power high voltage automated switchgear analysis function, which combines the STL algorithms with built-in intelligence for automated signal evaluation, making the operator's interaction minimal. For low power and low voltage applications, an automation sheet can easily be customized to adapt to almost any testing procedure. For example, you can customize selections for single, three-phase, or DC calibration, or short circuit testing with minimal operator interaction. Now, the user can select the appropriate test, then select the appropriate voltage range for the test, as well as the current range to be used. In most cases, users prefer the flexibility to customize their own STL switchgear testing and analysis. Therefore, the STL verification sheet is a very valuable tool in learning how the STL functions calculate on their own waveforms and provides a great method for starting the creation of formulas for custom analysis. Now, to give you an idea on how valuable this tool is, we're now going to focus on 3 examples on how to use the STL verification sheet to start the creation of your own custom and automated switchgear analysis. To get started, the Perception STL verification sheet requires the Perception CSI option. Here, we see that already installed CSI runtime, and of course you need STL. So once you've got that installed as well as the STL verification sheet, you can go to Manage Sheets. Under CSI, click STL verification sheet, click on the Load button, and you'll see a left column of functions from STL, RMS to Power Factor, and we're going to cover the more popular functions starting with the STL-Base Functions. Now each function has an explanation tab describing how to prepare and use the function. You can load an existing file by clicking and dragging traces onto the display, or in this case, we're going to go to the Preparations tab, click on Open Recording, and select Curve 1 for our STL test signal. Then we're going to use the default for available traces, and here is a typical current waveform with some exponential DC or asymmetric current. Now we'll click on the Generate STL Calculating Formulas. Here it's reminding us that any existing formula will be overwritten. If we click on the Formula tab, we'll see the automatically generated formulas, including signal start, end, next and previous, crests, and next zero crossing, and so on. To see how these calculations operate, we'll go back to the STL verification sheet and click on the Output tab and set cursor 1 to any particular position of interest. Here we'll notice that any calculated values already displayed in the sheet below, including next and previous, crest, and so on. And now we'll click on the cursor icon to set cursor 2 to any of the calculated results based on the location of cursor 1. Now to get more details, you can click on an info button and you'll see information similar to the STL user manual, which includes an STL documentation reference. Here's a handy tip. By clicking on the checkbox for Y threshold level, you'll see 3% full-scale levels on the display. Your signal must exceed these levels for STL functions to calculate. And if your signal's too small, no worries, just incorporate the function STL rescale into your formulas. We'll go to the Formula tab and we'll actually click on the Function Creator, work our way to the STL Functions, and to the STL-X rescale function. This returns a waveform with modified displayed scaling. And you can select your original waveform, type in the new upper and lower limits, or better yet, you can automate the process using calculated values from the max and min functions. Now just a side note, if you wish to see further details on any formula, you can click on the function to see at the top of the page a list of attributes, an example on how to use the function, and a short description. The next popular function we'll review is RMS Functions. I've loaded a typical STL test signal and now we'll click on Generate RMS Calculating Formulas. Here we're prompted to create a new signal where the offset is removed. You'll notice the waveform's offset is below the dashed 0 line. So we'll click on Yes, and an additional waveform without the offset is automatically created. Looking at the formulas, you can see the variable signal offset is calculating the mean on the first 10 milliseconds of the original waveform. And the new waveform called signal is created by subtracting out the offset. Going back to our STL verification sheet, we'll delete the original waveform that has the offset, and we'll change the color of the new waveform without the offset just to make it a little bit more visible. Going to the Output tab, we'll move cursor 1 just before the second valley, and then we'll click on the Calculate button. Then check the Show Slope Cursors box, and we will actually click on the previous 3 crest RMS slope icon. So here you can see lines that are appearing on the points used to calculate the previous 3 crest RMS, as outlined in the diagram on the right, with points ABC. And to the left is the RMS equation for reference. Now you can even click on any of the ABC icon buttons to move cursor 2 to any of the calculated points. And we can do the same for the next 3 crest RMS. If we click on True RMS tab, it's another way to calculate RMS. We'll position cursor number 2 just after the first valley. Then we'll move cursor 1 just before the last valley, and then we'll click on Calculate. Now, using the two cursor positions, it checks how many integer number of cycles are between the cursors. Clicking on any slope icon, you can see the change in the horizontal lines displaying the time period for the RMS calculation for either the previous periodical true RMS or the next. Now, the standard RMS calculations also displayed at the left for comparison. Also, the results from the formulas can be seen in the Output from Formulas tab. A popular function, especially in the United States, is power factor, which is part of the extended functions we've called STLX based on UL489. Now here I've already loaded low power current and voltage signals, so now we'll click on Generate Power Factor Calculating Formulas. So clicking on the Output and Symmetrical tabs for signals up to 10,000 amps will first deselect Enable Asymmetry Check, and then we'll click on Calculate. Now here we see a power factor of 97.16% and a symmetry of 9.384%. Now, normally that's too high because no more than 7% of symmetry is allowed according to the standard in order to have symmetry. Clicking on the red and blue cursor icons for first and second crest current, we can see where the calculations are performed. Now we'll place a check mark for Auto Skip Asymmetrical Crests and recalculate. Now asymmetry is 2.587% because it automatically skipped the first crest of current since the asymmetry is too high. Again, clicking on the red and blue cursor icons, we can see the new calculation area, which is shifted one crest to the right. Now looking at the formula database, we can see the current start and end are calculated on lines 9 and 10, and then on lines 15 and 16, we have the previous zero crossings that are calculated before closure on the voltage. Then the open RMS and frequency are calculated on the voltage. Lines 21 to 31 checks for valid crests on current and allows you to skip zero crossings. Now on line 35, we've calculated the frequency of current followed by symmetrical power factor on line 37. Going back to the STL verification sheet, we'll now look at asymmetrical power factor. First, we are going to load HP current as our signal for this particular example. And now we are going to generate the power factor calculating formulas. Now we'll select the Output and Asymmetrical tabs. Clicking on the Info button provides all the details on how this calculation is performed. In summary, various envelopes are used to get a ratio between the asymmetrical and symmetrical RMS components, and then, as you see here, a lookup table is used to get the power factor. Now this calculation is performed according to the UL489 document as shown here. And now we'll click on Calculate. We'll check the box for Show Envelopes and Show Asymmetrical RMS. And the power factor as well as all the results in between are shown. Clicking on the red and blue cursor icons will show you where the first and second timing points are located, as outlined in the diagram to the right. Clicking on the Formula tab, we see the asymmetrical calculations begin on line 70. Now T0 is the starting point, T1 is the second point, a half a cycle from start. On line 93, we have the standard asymmetrical power factor function. However, you'll notice on line 94, we've even added a function called asymmetrical power factor decimals, which provides decimal results in between the integer lookup table results. Well, that wraps up a quick overview of the STL verification sheet to help you get a start on creating your own formulas. If you have any questions, please feel free to call the HBM support team at 1-800-578-4260, or you can email support@usa.hbm.com.